So we started that? Okay, good. All right, so a little network thing just to start with. This is 1980, this is the Senate. These are voting patterns in the Senate. So there's a little network visualization. Blue and red have their traditional meanings. So this is the Senate. These are where people have voted in the same way. This is the degree to which they've voted. So yeah, so this is 2013, and then it's going to wrap. So this is 1989 through 2013. Yeah, I mean, it goes up. Like that seems a little more, and they vote more or less probably in different years. So there'll be other ways to look at this, but it does feel like it's.
How are they doing the colors? Because it looks like there's people with different colors. It's not perfectly black.
Well, so yeah, you're.
Oh, it's red and red.
Yeah, and there's some purpleness in the middle for people who have voted similarly. Yeah, right. So. This is 100 people, right? So that's one place where you can make a reasonable simulation. Not bad. What else have I got to tell you? Okay. I spent an hour trying to get an apostrophe to work properly. All right, so that didn't work out. Really tricky. Damn it. Anyway, the slides are in decent shape. Okay, so it turns out we have 4 lectures left. I was possibly thinking we had 6, but there's this whole Thanksgiving thing. Yeah. It's a bit different this semester, though, right? There's only 1 week or half a week after Thanksgiving. 3 days. Not that anyone is counting these things. Yeah.
6 months of graduation.
Okay. No, the full semester I usually have down 12 weeks, Thanksgiving, 1.5 more weeks. Like there's a real pattern to it, but I don't know what I'm doing anymore. All right, so. Okay, so. There's more in this set of slides that I want to tell you about, given sort of the scope of what we have left. I'm going to finish up some stuff on Contagion. That'll be today, roughly. And I want to talk about scaling next week. So that's a really big part of systems. We've talked a lot about power law size distributions, but this is about how things scale as things get bigger, right? So lots and lots of stories there. Lots of differences, lots of things to think about. But another realm of universality and that sort of story. Okay, so, and then there'll be a concluding lecture on the theory of anything sort of thing, right? So we'll do that. I'm trying to make a map of the course, so we'll have that. We had a good suggestion, because I was talking about, it could be sort of a Lord of the Rings type thing, so there'll be the mountains of power law distributions, which of course should look like this. So that was a peanut gallery over here, right? Yeah. Well, the mountains, and then the idea that they would be, yeah. Mount Surprise is the tallest one, right? Mount, I didn't expect this at all. Mount Financial Collapse. Okay. What is it? With monks, yeah, lots of monks. Monks looking very surprised. All right. Monks do not go here. All right. They pretend it doesn't exist. It's just that, right? Yeah, okay. So I'm going to touch on all of these. I'm going to give you a good overview of this work. It's now up to about 1,000 citations. Duncan, a piece that he worked on. When I was finishing my PhD at MIT, he was there for a year as a postdoc. So we talked about it a little bit then. But this was a nice piece of work, a beautiful piece of work about the threshold model that we've talked about with Granovetter, just simply put onto networks, right? So what happens then? So it's PNAS. Murray Gell-Mann was the character steering that one through, as is the way it works with PNAS. You don't have to do this, but if you have some big character who's part of the National Academy, that's a nice piece. It's changed. It used to be that your buddy could get you in, but it's a bit different. All right, and so we have some other approaches. I'm going to touch on these. I'll give you some visual candy for those, because there's some nice math. But I think that's going to actually be in complex networks, which is next semester at 2:30 p.m. for those of you who are keen as mustard to do it. 2:30. Did you hear that? Did I say that? It has been changed. Okay, good. Right, good. All right, so we're going to work. Now we'll just get into it. Social contagion on network. So now we're going to have various kinds of networks we'll think about, but of course to start with, we think about random networks because we'll do that. So the network's going to be sparse because that's representative of the real world. If you read Duncan's paper, which I advise you to at some point, if you want to think about contagion, it's sort of one of the classics now. There's a lot of defense at the start about what this could model because of reviewers and so on. So it has a good extra piece at the start. But again, random networks. So you're randomly connecting people up. You don't see this, right? This is one of the things simple part of random networks is you don't see clustering, right? So that's a very important part with the mechanics of how you figure things out for random networks. It's also a limiting fact because the real world is not like this, but it gets you a long way. So they're locally branching networks is the story, right? You don't have to worry about loops locally. There's some really crazy things some really interesting math. And it took about, well, I guess 5 or 6 years to get the big chunks together. So for example, you've got a particular kind of spreading happening on a network. What's the probability that it takes off? Well, 10 years even. Probability that it takes off. What's the expected size if it takes off? I mean, these are very basic questions. This is just random networks. Turns out that that's hard. Okay, and you can go off in the world of generating functions and do all sorts of craziness there, but yeah. Okay. You don't have to, actually. So, okay, so individualized is going to have case-by contacts. It's going to be the case that every link is a reciprocal, right? Link, so the influence goes both ways. So there's nothing special about anyone. No one is special. Good to remember that. So everyone's going to have a fixed threshold now, and as we saw with Granovetter, the key thing was actually having a distribution of thresholds. That's how we got that map of the interval that created interesting things, right? So we went from a threshold distribution to this cumulative, and that was how we could see things evolved, right? So we talked about fixed points and unstable points and so on. All right, okay. So, but now we'll get to the point where actually, even if everyone has the same threshold, it's the network structure that's governing a lot of the behavior. So, of course, we can have thresholds varying. We will do that as well. But it's fine to have, it's actually quite okay just to have there's enough to explore if everyone has the same threshold, which is odd, because they're varying in their number of friends. Okay, so here's what's happening. They're repeatedly polling their contacts, right? So you're sitting there in your network, you're looking at everyone, and you're calculating how many have Ugg boots on, and then you go back, and then you look again. There's a big clock, and it says, now look for Ugg boots. And it's like, now look, so it's a bit odd. But that's, you have to look at all these simple models that people produce. Are they discrete time? If they're discrete time, is it synchronous updating? Is it asynchronous? Very different things can happen. So if someone's telling you a beautiful story about their model, you have to look. Lots of benign looking assumptions. So that's what's going on here, often floating around. Okay, so very simple thing. So an individual will become active, right? They'll start to wear Ugg boots. If the fraction of people they see wearing Ugg boots, maybe, do we need a different example? So exceeds their threshold, right? For this particular thing that's spreading. Okay, surface tablets. Okay, no, it's not going to work. And then they'll remain active. It's an SI model, right? So if for some reason, so no one turns off. Okay, no one turns off. We could add that as well. Never go back. You're always known as an Ugg boot wearer. What's that?
That's kind of like more in line with reality. Like, you don't get Ugg boots, see so many people wearing them.
They do get old.
Yeah, things fade away.
But do they? Because
Okay, we're talking about lots of different things here. We don't want to go cheap on the Ugg boots. Yeah, sure. Well, look, Ugg responds magnificently, when it takes off. And they'll produce, Puma did the same when their shoes took off. Suddenly it's like, every model we've ever made is now, and the shops all want it. So that helps, but it's going to burn out. It's got to burn out.
We could make this a really relevant topic of methane copper, how it's so popular, right? How they're stopping sales at their
I see.
location because
They want to keep it under control, right?
well, it turns out it's because there's too much crowding in the neighborhood, so there's traffic that's disrupting, like your left turn out.
So it's not for marketing purposes. It's just for so locally no one hates us, basically.
That's the idea. So now, is it being pushed away someplace else?
Probably not.
But you just talked about it, so that was good. No, people recover from, you've got to let people recover from Ugg boots. You've got to forgive them for that. There will be photographs that people will look, I mean, look at photographs of, anyone going back in your family or whatever. It's just not good. It's not good. It's never good. It's like, how did everyone want to wear these things? I mean, 70s, 80s, whatever you want. It's just, it all seemed fine at the time. Everyone else was doing it. And now it's just hideous to look at, generally speaking, right? 60s? Oh my God. Okay. All right. So, but when you're in it, it's totally fine. All right. Of course, a fashion icon, so I know about these things. Okay, so, right, let's have an example. So everyone has a threshold of 0.2. So 1 in 5, or 2 in 10, or 3 in 15, they're going to switch, right? So this character here has switched on, right? So they have 5 here, and let's imagine that at t equals 0, they saw someone wearing Ugg boots. So now they've donned a pair. So at the next time, the arrows are a bit deceiving because this is the way it's to indicate the way it's spreading dynamically, but really the influence goes both ways. So there's this one had a 1 in 3, so yes, they're on. Okay, I'll just say this one. This one was a 1 in 5, so now they're on. And A feels even more reassured. Right now they're 3 out of 5, so they're like, yes, it was a great decision. Yes?
Are we allowing triads? You made it sound like
Oh, this is just one little example. So the analytic stuff we'll do first is for pure random networks. And then we move out to things with groups and so on. Yeah. Analytically, you can do this. As soon as you introduce some real world complications, it becomes very hard analytically and you move to simulations, typically. But everyone tries to they get as far as they can analytically. We'll publish as many papers as we can on an analytic result just because we can. All right. Okay, so in the next, this character had 2 of 8, so that exceeds right? So it's 0.25, so it's over 0.2, so they're on. And this one's resilient. Somehow, maybe we'll get them later on. Okay. There's been some very nice work recently. I mean, one of the things we talked about very early on when we were doing this work, lots of people have done things, but 2001 or 2 when we were thinking about social contagion, is that influence coming from different sources is very important, right? So, and there's some nice evidence for that. Uganda and company at Cornell and Facebook did some nice work with it, Facebook adoption. Just not how you behave once you're on it, but actually just signing up for it. So people with a more, there are other examples, but this is a good, that may conflict with this, but it's a good data, obviously a good data set. So they got out this result that if you have more diverse set of people who are already on Facebook, that enhances your probability of adoption, right? So you could have 1,000 people, but if they're all from your high school, that's not as good as having, 1,000 people spread across 10 different things, because it obviously feels much bigger. But they're able to, so it's a suspicion you might have, but they were able to quantify it and show it. Very, very nice work. Anyway, this doesn't have that. I'm just trying to tell you more things. Yeah.
So the threshold that you went to is fixed for the whole.
Everyone has the same one in this example. Yeah, and it doesn't change in time.
Okay, but are there models where the threshold, maybe the threshold is a threshold for, I don't know, like a certain, like, how do I want to say it? When a certain number of things are turned on in this time,
Mm-hmm.
that maybe that would switch something else and the threshold would change, or
You can certainly have evolving thresholds. Yeah. It just turns out that the models are so rich with just fixed thresholds. You have to go through that first. So the problem is, once you want to step beyond this and really get into more complex things, you have to start saying, well, what's the real world like? Because the adjacent possible in terms of models is just huge, right? So you could say, let's add this whistle, which is totally great, but and there are many, many things you can think, as you said, very, very reasonable things. It's just now you have to think, well, maybe we should just find out about reality a little more. However, maybe the model you think of has really cool fixed points and nice math, and that's what happens a lot, right? So people get excited about it. Yeah, publish a paper. But it's good to get to reality. But we'll get a lot of so as long as the pieces that you add are really big, gigantic kinds of pieces, then that's fine. But at some point, you have to say, let's try to capture the real world. Very, very hard, right? I mean, how do you measure thresholds? Really hard. I mean, even as to whether they sort of exist in this extreme way. So these are extreme thresholds. Off or on. Okay. All right, so we'll study random networks first. So we're going to have talked about these guys, n nodes with degree distribution, little p for some reason. Oh my God. Trying to make it uniform. Okay, so we talked about this. We randomly connect the nodes, blah, 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 and we want to see just when things will take off. Right? So we could ask different kinds of questions. What if we seed 10% of the population, 1%, 0.001, whatever it is? What if we just turn one person on? And so that proves to be a really interesting thing. Just what if we just switch one person? So we want a cascade condition. Under what is this network, like a forest, is it ready to burn, right? If we put the match in the right place. So, right, one individual is activated. What's the probability it will take off? So so it's typical kind of phase transition thing. It'll be 0 if the thing is not ready to go. It'll have some small probability. And you could imagine just a switch thing, right? It's sort of first of all, there's a yes, no. Can things take off? Yes, no. The next one is what's the probability, right? So the next one's a bit of a harder question. You can tackle them analytically in different ways. So, and what about the network and this threshold distribution, if there's even a distribution? What do we know about those things, or what do we need to know about those things to determine this global condition? What's really a global condition? Okay, so here's a sketch of the story. So imagine this is our whole network, as I've carefully drawn a network here. This is our system, and I'll try and give you an idea of how this is going to blow up. Okay. Why aren't they little? What's that? Stick figures? This is a little bit of a network in here. These are matches, right? So you could try and put your match in different places, and this is where it would. This is how these pure random networks with arbitrary degree distributions work. So what we'll see is this is not always true, but if it's a system that can explode, it'll have this structure. There'll be a giant component. It's not the whole giant component, but there'll be a macro component. So if you look at the whole network, you could actually see it. It can be quite small, but you could see it from a global perspective. And these characters in here are such that, and we'll get to them, so they're vulnerables. It means that they just need one friend to start wearing Ugg boots, and they're like, yes, right? So these are the easy, they turn over very easily, and so anything that gets them will spread. If you start with one of these characters, or if you start with someone who's outside but connected in there, so they're not an easy switch themselves, but if you pay them some money and they put on some Ugg boots, then they have a friend in this vulnerable subcomponent, and it spreads through here, and then it's possible, and so this is a slightly different subnetwork here. It's disjoint from what I'll call the triggering component. So there's a triggering component which includes all of these vulnerable, gullible, sure, whatever kind of characters, right? And then these ones who are connected to them. There's a final size which has to include the vulnerables, right? Everything spreads through there, and then maybe some characters out here that need 2 or 3 hits to switch will switch as well. So that kind of makes sense. So it's very funny, strange things happen for these kinds of networks. So all right, so this is the story. So the final is the potential spread. So if you'd started out here, outside of the triggering component, you switch this character, even though they might have lots of friends, they're not connected to the vulnerable component. So nothing spreads from them. Mm-hmm.
So is signal final the best you could do in terms of contagion?
Yes, for this particular system, right? With the thresholds as specified.
For the system, given initial match location, this is the best you could do.
Okay. So if you're outside of the triggering component, nothing takes off. Maybe you get a couple, but it dies out. If you're inside the triggering component, it spreads. It always spreads to this.
With the same
I mean, you could have a more probabilistic one, but we're thinking about a deterministic response function.
Okay.
So this is purely deterministic, actually. Yeah.
All right, so it's dependent on where you stick the
I will eat some banana. Uh-huh. Good. It depends, yes, absolutely. Yeah. You can't just throw a match in anyway.
get the same thing.
So what's kind of cool about this is that one person, one individual, everything can blow up from one individual. So this is a very fragile system, right? Just someone accidentally wears Ugg boots. Returns from a trip to somewhere, not Australia, somewhere, They're from Australia. No, but not outside. This is something I've wanted to emphasize as much as possible. Yeah. Because no one has indoor heating because it doesn't get that cold. Yet you freeze to death in winter because no one wears hats and it's 25 degrees or something. And you wear shorts playing sports and stuff. So it's actually much colder than a place like this, where you just crank the heat through the roof, as soon as it gets to 45. Destroying the world, of course, Vermont is, yeah. Okay. So what do we think about this? Kind of a funny thing, right? Okay, so let's dig into this and see how it works out. Okay, so this is how we can think about this spreading, right? So we're gonna turn on one of these characters and see what happens. So it's actually much better to say, okay, imagine this link is emanating from an infected, Ugg-wearing maniac, and we want to see, well, what happens? Does it spread past? Does it switch this character and then spread past them? All right, if it switches this, then we can think about, well, now it's got all these more outgoing edges, right? So this is a reproduction ratio, if you like, but at the level, it's much better to think about edges than nodes. The natural thing, because we are humans, is to think, I'm infected, how many more people am I going to infected? You want to think about, given this friendship connection, that's an infected link, wearing the Uggs, this poor character over here sees it. How many more people are then exposed to this horrible disease, right? So it's about, do infected edges, what do they typically get, right? So if one infected edge on average gets you more than one, then it takes off, right? Because it's going to cascade through. Very simple growth story. Yeah, there's a little bit of that. Yeah, that was pretty slippery because it was actually really a grid, and it turns out that magically works, and you can't do it for square lattices, but it's actually it's easier in a way, although it took years to figure out how to write this down properly, but it is, it's very ally. Okay, so what I just said, so if an infected link gets you more than one, then the thing can spread, on average, 1.01, doesn't matter what it is. All right, so we need to understand which of these nodes have that property, ones that can be easily infected by, or readily infected by one neighbor being on. So this is the term, it's actually from Duncan's original structure, we'll use it again, we tried to come up with other ones, but vulnerables, all right. So if you can be switched on by just one friend wearing Ugg boots, pretty bad situation, you're a questionable human being. If that's all it takes, then you're vulnerable, right? So that condition is pretty simple. It's just simply you have a threshold, right? You have a threshold. Before we had 0.2, for example. So if your number of friends is 5 or less, right? So 1/5 is equal to 0.2, 1/4 is 0.25, a third is 0.3. Then you are vulnerable, right? So if you have you need 6 friends and one friend wearing Ugg boots, then you have 5 others, and you're like, yeah, okay, it's not enough. So, no, the decision is always made about fair enough, but this decision is always made about you look at all your friends. This is going to be about the other friends you have.
You don't have a super cool friend?
Right, you don't. This is a natural complication that we could add. Some people are super cool, so what about that? There's also, you don't want to copy your friends because that's psycho, but, right? Exactly, so you copy them a bit, But you can...
Everybody would copy her.
But you copy, maybe, right, all right, okay. So, in general, right, so your number of contacts has to be like this. So this is, we're just going to switch this around. 1 over phi is greater than or equal to k sub I, and then we'll take, this is the floor, right? We want to turn it into the integer below this value. Right, so 0.2 becomes 5. The floor of that is 5. Okay. 0.18, it's the same thing because it's 5 point something, so same thing. Okay, so we'll see some discreteness kind of affect the network. So it's very subtle because so it's true that 0.18, it's less than 2, that gives you, the vulnerables all those who have degree 5 or less, but when you get out to 10 and 15 and 16, 20 friends, then you can get some switches, right? Because someone might need, I don't know, instead of 4 out of 20 of their friends switching, it could be 3 out of 20 because the thresholds are different. So when we're talking about these higher level characters, the ones who need to switch because of more friends, okay, doesn't matter too much. Okay, so simple story. So if we want to have a global cascade, and we have this, I'll just erase this horrible mountain. Right, so we have this vulnerable component. So everything can potentially spread out of here, but if we put our pair of Ugg boots in here, right, so we light the thing, right, in here, it will spread at least through this little subnetwork. There's also this possibility of getting someone in the triggering component, blah, blah, blah. So the thing, if this is large, then we'll see at least this set will get infected. And so we'll have a fraction that's non-zero, right? You could have 3 vulnerables connected together, but we're in an infinite network. You get one of them, you get all 3, but that's not enough, right? So you need a, what we'll call a global cluster. Connected cluster of vulnerables. So you have to figure out if your network has that or not. This is only for pure random networks. It doesn't generalize, which is very odd. Okay, you might think this is everything. So this internal, this connected group of vulnerables, that's a critical mass. So now we have this very nice thing where one node can trigger the critical mass. So you have this kind of critical individuals. So you have this really nasty tinderbox, right? If that thing gets hit, very Achilles heel-like, if that thing gets hit, this so-called kind of critical mass will go through that. And at the meantime, some others who need 2 or 3 or 4 or 5 hits start to get infected and it spreads through them. So this becomes a very hard problem to think about if you do it in the wrong way, which many of us did for a long time. This is getting all of these guys who need 1 hit. What about the ones who need 2 and 3? Like, how does this thing go through this whole network? All right. Okay, so we're going to follow a link. We have this story before, so if we randomly choose a link, so we're going to randomly hop on a link that's infected, the node that it's connected to will have a degree k with probability proportional to k times p sub k, because there are k ways to get to that node, right? So we had this odd story that means your friends have more friends than you, which is really disappointing. Okay, okay, so we've had this. We have normalization, the average of this thing. Right, so if we just sum all of this up, this is of course just the average degree, right? So we can normalize this guy, we divide it by the average degree, and we get our probably the node that we run into has a degree k will be this, right? So if this one gets turned, then there are k minus 1 new edges, which is connecting to what you were saying, I think, right? So if this one flips, then there are k minus 1 new infected edges. So if this guy only has 1 friend, then that's it. There's 0, right? Nothing comes out of it, so we don't worry about those. If it has 2 friends, then 1 more. If it has 3 friends, then there are 2 more from that guy coming out. So that you need to be connecting to nodes of degree 3 and 4 and 5. Which totally makes sense. All right. Vulnerability of the node that you're linking to. So there's different pieces, right? So we're linking to this node. It has degree k with the probability we just expressed. Here's the probability that it is infectable. So imagine we have we'll generalize again. So imagine we have a distribution of thresholds. So they're all randomly chosen. I mean, you could imagine them being some probability distribution where they're connected to the degree of the node and all sorts of things. But let's just say we make our network and then we go to every node and we have a bag of thresholds and we pick out, or distribution, we sample from it and we give that node that threshold. So just as we did for Granovetter. All right, So if we integrate from 0 to 1 over k, that gives us the probability that this node, which has degree k, has a threshold less than 1 over k. So it will be switched on by one of its friends being on. Right? So this is the fraction of nodes of degree k for which 1 over k is greater than or equal to its threshold. Right? That's what beta k is about. Is it fair enough? Exciting. Okay. But you take your distribution, you turn it into beta k. Well, you're going to have beta 1, beta 2, beta 3, beta 4. It's just a bunch, right? A little sequence of numbers. So this horrible mess goes away. In principle, you could have different f's that lead to the same guys. Right. Okay, so if we have a linked node that's vulnerable, okay, that's a probability that's vulnerable, then we're going to get k minus 1 new infected edges, and we can put this together, right? And if it's not vulnerable, we have no new active links. Fair enough. Simple thing, right? So there's two possibilities. 1 minus beta k, beta k. So this is, we'll put everything together. Let's see if we can understand this guy. Change my font. Damn it. Okay, so can you understand this thing? So this is the simplest result we can produce for generalized kind of contagion. What is this mess? All right, so this is the gain ratio for one infected edge. Got this infected edge, we're in a random network. So it's hitting a node of degree k with, this is the probability that it hits that node. This is the probability that node is vulnerable and therefore switches, puts on UG boots. And this is the number of new infected edges that arise from that transition, right? And then we sum over all k. And we just have to go from k equals 1 up. And even k equals 2 up works, but k equals 1 up. Okay, all right. So this will give you the so we've got this infected edge. Just we pick a random, we're surfing on an infected edge, and we want to see how many new, on average, how many new infected edges that's going to create. So we run along the edge, and we run into a node of degree k with this probability. This is a function of these pure random networks. We have this quantity, which is the probability that that node is then vulnerable, which is to say that its threshold is less than 1 over k. Because it's just sitting there, doing nothing, and it's like, well, UG boots. Boop, puts them on, right? And now it's exposed this many new other characters, right? The thing is spreading through the network. So these are probabilities, this is a count. This is k minus 1 new edges. And we sum over all k, so we get this is the expected number of new edges, right? Probability, quantity that we're kind of trying to find an expected value of, that's a way to think about this. So the probability is made up of 2 bits, and then there's this piece. You can generalize this very nicely for all sorts of things, for networks that have assortativity, that have all sorts of different kind of connectivities and so on. It's a paper that came out of this class, actually.
Why don't we start at 117?
Yeah. No, you're right. Yeah. That's right. So this vanishes, so it's taken care of. Yeah, but you're totally right. Yeah. So this is the physical kind of description, k equals 1 to infinity, because you could connect to a degree 1 guy. Yep. And then you could and then the next step would be say, okay, we'll just put 2. Yeah. Which may or may not help depending on what you're doing with it, messing around with. Yeah. Okay. Yeah. Well, I'll show you some things. Okay. So on the other hand, right, this is probably you connect to a guy of degree k. This is probably that guy does not have is not infected, is not vulnerable, right? And as a result, there are 0 new infected edges coming out. So this is, it's easy to leave this piece off, but this is just, so now we've combined everything, right? This probability plus this probability gives us everything. That sums up to 1 by itself, right? This is good. And these are the two things that can happen. So this is failure, and so as a result, this goes away, and we're left with these 3 chunks. And in general, you can do this, right? This is the connectivity probability, the infection probability, and then the kinds of the count that comes out, right? So it could be, these nodes could have flavors, they could have all sorts of things. It could be all sorts of other characteristics. But this is a bare random network with arbitrary degree distribution. So this is a nice result. This is one, we're not there yet, but this is one thing. This k minus 1 and this k are a bit of a crucial piece, so we'll get to those. Yeah, because it's about the number of, so you're on this edge?
Yeah.
This guy has degree k. There are k minus 1 new infected edges. So one edge. Yep. Yep. So it's edge. What's, how many new infected edges does one infected edge beget? Right. So that's the growth ratio is from edge to edge number to edge number. Right. Good. Yeah. Good. Yeah. Okay. So so when it's equal to 1, I guess I shouldn't have equal to 1. When it's greater than 1, then it does take off. At equal to 1, it's right at the edge and sort of trickles along and is a bit dangerous. But greater than 1, so if the number of infected edges is growing, right? One edge is getting on average more than one edge. Then, if it's 1.5, 1.5 squared, right? It's growing. Exponential growth. So it's pretty bad. This doesn't tell you at all about the final size, because that is a tricky thing to think about. It'll tell you about how this is just a statement that it will take off. It doesn't even tell you what the probability is. Okay. So let's have some special cases. We'll simplify things in interesting ways. So one is, let's go back to just sort of a disease-like spreading. So now it doesn't matter how many friends you have. If you see someone with Ugg boots, you just switch on with probably beta. Right? It's independent of, you don't worry about your other friends. And there's this one-shot sort of thing. So in that case, the beta sub k just comes out here. We have beta, and we have this result. And we can simplify it even more, and then this will help you understand this one. If beta equals 1, then everyone just gets infected, right? Just spreads. So this is a different condition. This is actually the giant component condition. This says that everyone is vulnerable, everyone gets infected. This is actually a graph theory type state. This collapses back to a graph theory result, which is whether or not you have a giant component in your network, in your random network. This just says that when you look at, so if this is, right, so you take your distribution, there's no disease spreading mechanism here anymore, you compute this quantity. If it's greater than 1, then when you look at this network from a distance, you'll see a giant component. So which is a fundamental property of networks, whether things will spread or not, right? You need to have a connected group. All right. Okay, so let me explain what happens then on random networks. This is good. Okay, so this is a version from the Watts paper. And let me explain some things. So Z is average degree. That's sometimes the notation, right? So this is average degree. What we're doing is, as we vary across here, we're constructing these are just pure random networks. So the degree distribution is Poisson. Edish-Rennie random networks, right? So it's just pure random wiring. So we're just looking at those guys. And if you remember with them, there was the threshold for a giant component was average degree is 1. So when the average degree is 1, you start to, and above that, you start to see a giant component, right? So here's an example of the largest component at around 0.5, right? It's nothing, no good. At 1, you start to get these kind of spindly, funny-looking things. They're fractal shapes here. And then this is at 2, very clear giant component emerges. At 4, it's just a complete disaster, right? And there are a few extras out here that aren't connected. So this is just the biggest component. This one only has, whatever it is, 5 or 6. There are some little blue dots in there. There are many, many tiny little components that aren't shown here. Right? And this one similarly, but there are much fewer here, and then many, many fewer here. Okay, so this is what the networks look like. So you think if you're on this thing, everything spreads, right? Okay, this is why it doesn't happen, because we're talking about these threshold response functions. And so in this case, we're going to have thresholds. Everyone's going to have the same threshold. It will be basically 0.18, right, for this example. So if you have 5 or fewer friends, you are vulnerable, right? And here's the story. So as we tune across here, first of all, there's no giant component at all of any kind, so nothing can really spread. So nothing spreads. So this is the final size, is in red here. So as we go above 1, well, now we have a giant component, and many of them have very few friends, right? They have 2 or 3 or 4 or 5 friends that are in this giant component. Some have 7 or 8, whatever it is, but most of them are vulnerable. So the giant component is mostly composed of vulnerables. So if you hit that thing, it spreads all through the giant component. So the fraction, this is the largest component size, the fractional size, this is a fractional size here of the network. This is the size of, the fractional size of the largest component of vulnerables. So it's growing, and in fact the final size of the spread is the same. But then this begins to depart as you get up here, and there's a very interesting thing happens at this limit. So let me try to explain this. So let's just think about the vulnerable component as we increase connectivity. Well, you're adding more and more edges, right? So nodes are getting 3, they had 3 friends, now they have 4, now they have 5, now they have 6, 7. So as they go above 5, they become non-vulnerable. They're not vulnerables anymore, right? You need to have relatively few friends. So the largest component is actually getting smaller and smaller and smaller. You're getting up to this giant hairball everyone has, you know, out here, whatever it is. You know, this is 7. Way out here, you have everyone has 100 friends on average. And there's some spread around that, but it's not a very big spread. So no one is vulnerable out here, right? So the size of the largest component of vulnerables goes to 0. And that happens abruptly, actually abruptly. This is just some example, but for a finite network, but it actually analytically goes for an infinite network. Fair enough. So it's well connected, but if you try to find this big well connected network, you find the vulnerable component, this little critical mass, it evaporates. Because think about, one way to think about this is you're not actually building networks as you go across, but imagine, nodes are just getting more and more friends, right? So they just become more aware of the world. That's really one way to think about it, right? So if you have 50 friends, now you're sampling from more of a population, and you become less susceptible with this. No, this is a fresh community that doesn't quite understand what it's doing. So right. Yeah. Well, what's happening though is out here you've got 50 friends, and you see one friend wearing Ugg boots, and you're like, well, that's another thing. You need to get to 5 or 6, and you're like, okay, now I do it. 10. How do we feel about this? So there's more to this, but let me. So this is the size of the largest vulnerable component, the tinderbox, right? The little bit that can go bang. It's nothing here, and it's nothing out here. Right, so, but in the middle, yes, we've got some good stuff. All right. Now, the final size that it spreads to, though, is very different, and that's, so for a start, it tracks the vulnerable component because they're just exactly the same. Because the vulnerable component, a lot of them don't, the giant component, a lot of them don't have more than 5 friends, right? So, but once we get out here, so we're getting to this limit, the vulnerable component is getting smaller and smaller, but the whole network is getting more and more connected. This is not obvious that this would happen, but it turns out if you hit this vulnerable component, this little Achilles heel, then it spreads everywhere. Right? So the ones who take 2 hits, 3 hits, 4 hits, 5 hits, they all get hammered. But then we switch, there's no vulnerable component anymore, right? There's no large scale one, so you can never switch this thing on by hitting one person. So that's here. So the final size goes straight to 0. So this is a really dangerous transition here. So you're here, and you think you know what the mechanism is. You know it's a threshold mechanism. You look around, you're like, oh well, everyone's got 7 friends. On average, not many people will switch, right? There's a few vulnerables, but we can see they're not connected together. We're safe, right? But as you draw back, you get to this very dangerous point where it's looking okay. But if you just get the right little, this little component, there's a tiny little fraction. They all hang out together and they're like, I'll do what they do, sure. And they go through them. And then it gets the 2s and the 3s, and the ones who take 2 hits and 3 hits and 4 hits and 5 hits. So it depends what's spreading, right? And you know, I mean, there are lots of different things. So it's a robust yet fragile. And really, yeah, ignorance facilitates spreading, right? You need 2 things. You need to have connectivity for a start. Nothing can spread. Out here you have sufficient connectivity that people are actually watching enough of the world for this particular spreading mechanism to fail. If it's a mechanism where just one of your friends gets infected and then you're like, sure, you know, like you're open to everything. It's not a threshold thing, it's more disease-like. Then, of course, it gets worse as you go out here. Right? But if you have this threshold type contagion, then it completely changes it. So hubs, in fact, so the hub story, hubs are a real barrier to this kind of spreading, right? So if it runs into someone who has 10,000 friends, and this person sees one person doing something, they're not going to switch. They're good starting points, but of course hubs are very hard to influence. They're good starting points, but because suddenly 10,000 people are exposed to it, but they block these things, this kind of spreading. Right. So how are we doing with this thing? Basic consciousness. Okay. All right. Okay, so let's imagine then we have all of these random networks here, and we have, so again, this is the average degree going up to 30 even, and this is the threshold that everyone has. So this is a uniform threshold situation. We were just at 0.18, so that's that little picture that you just saw. It's a cross section now, and there's this idea of a cascade window, which is as we vary these 2 parameters of the system, again, it's just random networks, the average degree of the network and the the fixed threshold that everyone has, we get this opening of this we get, for example, in the first place, we get this feature that there are cascades possible here, and outside of this shape, there are none. And the reason is, there are these 2 reasons, right? So down here, the network is simply not connected enough. Their average degree is too low. It doesn't matter what your spreading mechanism is, doesn't matter. Nothing's going to spread. At the upper limit, now we've got people who are resilient because they're watching enough people. And the width of this thing opens up as the threshold decreases. So this makes sense, and it has these steps in it because of what I was saying. There are actually these little micro steps, but there are steps in here which are a function of, right? So if we were here at 0.18, 0.2 and 0.18 are the same, so the vulnerables are all the same down to whatever it is, 0.16. So this is when you get to a 6th. Now this transition is now anyone who has 6 friends is vulnerable as well. Now anyone who has 7 friends, 8 friends, 9 friends, they're vulnerable. So it makes the thing more spreadable. Okay, this is cool. That's another version of it because you could do it. Okay.
Did you do this?
Yeah, I don't know why I did that. Okay, I was just trying to make it understandable. I'm happy to have failed, but I tried. Okay, all right.
You needed whatever candy.
The GIMP. I use the GIMP, which is appealing in the name. You're right, right. I need some visual madness. All right. So let's connect these 2 things. So we had the threshold model of Granovetter, which is about all-to-all. So everyone is watching everyone else. You can think of it as a network kind of situation. And now we have random networks. So in the all-to-all network situation, or now you just think of an infinite population, you see what everyone else is doing, and it comes to you as an average number. Then you have this kind of behavior. So once again, this is the threshold. This is an example threshold distribution, right? This is the little f here. This is the integral of it, capital F. This is a cumulative distribution. As I discussed the other day, you have this map of the interval story, right? So if we started here, this one takes off. Boom. This is a critical mass model. If we start here, it disappears. This is a bit of a funny little example, but it disappears, right? So you need to, this is a situation where given you start above this fixed point, you do that some other way, right? You educate the population, you pay people. Then this little internal social copying thing happens and it takes off and everyone gets on board. So you can see what's going on. You have no real true believers down here. You have not many people who are very hard to change, but there's a hump down here. All right. And this is an alternate example where the distribution of thresholds is like this. So lots of gullables, lots of hard to turn characters up here, the grumpy ones. And if you integrate this thing, you get a curve going the other way. So it has a fixed point in the middle, right? So you always get a little takeoff at the start. These guys all get infected. They're like, sure. But if for some reason you started above that fixed point, they're like, really, no. And they give up. Okay, all these guys, they switch off. Yeah. Yeah, they need everyone. If everyone is doing it, right, there is a fixed point here at 1. It's unstable. But if everyone's doing it, they're like, okay, right. But that's what these characters need. They need everyone to do it to stay on. If it's just a fraction less than that, some of them will give up, and then more will give up, and more will give up. So different models. So if you have this threshold distribution and this threshold distribution, you put them on a random network, and there are, here's the average degree going across here. So the same threshold distribution is being used here and here. So the average degree is growing out in this way, right? So out here at infinity is this model. Because out here, everyone is friends with everyone else, right? No one is special out here, right? And then you get this kind of mechanism, and that's true out here as well. So this is the picture I just showed you, this very strange thing. So here's the fraction of vulnerables, right? In the largest vulnerable component. Here's the final size of that spread. And so what's happening is once you get above some fairly small value of average degree, now there's no vulnerable component anymore. And no one will switch on if one person switches on. So this is all about whether one person can break the whole thing, right? And that's exactly makes sense here because this is a critical mass, right? One person is this tiny little epsilon here. It's 1 over n, n goes to infinity. That never starts anything. But it will start this one, right? You just need a little fraction here and it will take off. So this is, it's all about whether the derivative is greater or less than 1 in this mean field model. And so you can see that that's okay here because here's the final size, which comports with this. That's the fixed point is a half. And this is the largest vulnerable component. It's getting smaller and smaller because it's becoming more and more connected. But with this kind of threshold distribution, you'll always have a little vulnerable component and things could always take off. Okay, so this is the story we have, right? I've told you these things, but it's a summary. No cascades take off because of the network's poorly connected. That's low average degree. High average degree, we have a giant component. Intermediate, this is where the interesting things happen. And you can have giant cascades from very small seeds. Okay, we're going to jump that. Okay, the final size is a very interesting piece of work. James Gleason led this work in Cork, actually. He's in Ireland. He went to Caltech, and this is some work that he produced, I think, during that time. But anyway, so he does a lot of really interesting, good work on spreading on networks and all sorts of stuff about networks in general. So, very simple question. What's the final size? Okay, so now we have just this condition, right? We have a cascade condition. We've been able to understand it a little bit, and there's lots more to it, I guess, but we'll get into that in complex networks. So the real problem is trying to understand, it's spreading through these vulnerable nodes. What about these ones that take 2 hits, 3 hits, 4 hits? What's the sequence of that? How do you figure about it? So a natural way to think about this is, thinking about expanding out from that point. And it turns out you want to do the opposite thing, so I'll explain that. Very beautiful work. So this is actually in Physical Review E, it's 2007. There's more work that came later on. This is quite in depth, so this is a good thing to look at, but I'm not going to give you a problem set on it. I could have. I guess I'll put optional on it. Okay, so all right, so this is a slightly different thing. All right, so let's think about this. So we're going to randomly turn on a fraction of nodes at the start, and it could be 1 over n, but it could be just 1. But let's turn on a fraction. Again, we use this local branching story, right? But we're going to do a different thing. So I want to just take you through the thinking here. I think, yeah, I'll save the horrible stuff for the beautiful stuff for complex networks. So let's think about what it would take. And the beauty here is that you actually solve the complete thing. So you get the number of nodes that are infected on average at time t, not just the t equals infinity limit. Okay. I mean, once again, simple model, need to understand it. You know, if we can't understand random networks, we get upset with ourselves. Okay, so t equals 0. This is how it can work, right? I is one of the seeds. And that happens with probably phi 0, right? That's how we're seeding this thing, right? So that's the start. T equals 1, I was not a seed. This is when it, you know, how does a node become active for the first time at t? So if t equals 1, I was not a seed, but one of its friends was, and i's threshold is now exceeded. So it has to be kind of a vulnerable guy, right? This is then, because it's going to be a sort of a sparse thing, this is a different business, and I'll have some visualizations of this, but at time t equals 2, this guy switches on for the first time. It's not going to be about these ones, it's going to be about the friends of friends, right? What they're like, so maybe it's like this. So these guys may have switched on with probably phi 0 at time t equals 0. The effects of that come through in 2 time steps. And then the next ring out 3 time steps, right? So, but it could be that this one switched on and this one switched on, and that comes through. And so now we can accommodate this problem. The 2 of your friends or 3 of your friends may be on at time t minus 1, and therefore you have a chance of switching on at time t. So instead of this is about moving out, right? We think about moving out from the seed node. This is actually about, let's pick a node in the network and let's see, you know, do the zombies come for it, right? How does its existence, or, you know, undead existence kind of we move from ugs to zombies again. All right, so how does that happen over time? All right, so that's his story. T equals n, right? So enough nodes within n hops away from I have switched on such that that's cascaded through, cascaded through, cascaded through. So that's the setup, and we can actually write down the equations for this. All right, so here's I was drawing a little bit of it here, but here's an example. So here's I. Let's imagine that this guy switched on at t equals 0, and these characters as well. So they are 1, 2, 3, 4 hops away, and a threshold of a third. Okay? So a threshold of a third. So this one will need 2 out of 5 to switch on. So it has 1 out of 5, so it's like, right, doesn't work. This one has 3, so you can see it's going to switch on. This one has 3, so it's going to switch on. This one actually has 4, so it doesn't change. The next time step, we're here. So this t equals 1. So now we're going to get this one to switch on, and this one will switch on. It's going to a little bit back, it looks like back cascading, but it's not really. But this one will switch on because it only has 1 friend, so they're like, yeah, whatever you do, I'll do it. Now this one has 2 out of its 3, so it definitely switches on. And the last time step, I goes, right? So this, we have to think about this analytically, but this is the okay? Yeah.
Why does the one that's on near I?
This guy, yeah.
Yeah, because the threshold's low enough.
Yeah, so this one was switched on exogenously at time t equals 0. Is that? and its effect on I, it doesn't have any effect on I until, okay, so this is the start. Yep. And so,
that one is in the same state as the other red one.
yeah, yeah. Ugg boots, Ugg boots, Ugg boots, Ugg boots. And so it's just sitting there. It's having some effect on these ones that we don't see. It's a once you switch on, you stay on situation. So boom, boom. Now I is like, oh, okay. 2 out of 5. It's a real thing. Switch. So the next time step, this one would switch. It depends what's going on out here. So so we're starting with some fraction of the population switching on, not just one person. But we can take that fraction to 0. And then it becomes the fraction of people around you becomes sparser and sparser and sparser. Is that
I guess I'm just wondering why the ones out here have this backwards effect, the one that's so close to it isn't having that backwards effect.
it does have its effect now. It isn't, like, I is aware of it, but it's making this calculation. It says 1 in 5.
Below the threshold.
Yeah, that's right. That's right. So it says 1 in 5, that's less than a third, it's like whatever. 2 in 5. Yeah, that's right. It is having effect the whole time, but yeah, right. I is aware of it. That's right. Yeah.
When you said it goes to 0, is there some like epsilon greater than 0 argument here that you can make? Is there some proof for that?
That
You know, like things go to 0, you say like, this has a small epsilon greater than 0. There's some like, does anyone prove that?
I mean, yeah, you'll see that the limit, you can see.
There's a limiting behavior.
Yeah, absolutely. Yeah, right. Right.
Still doesn't matter.
Right.
Fantastic.
Right. Well, I'll show you. Okay, all right. So here's a more elaborate, ridiculous kind of thing. Not sure. I guess I did both of these, so I have to show you them. Okay, so same story. Now we have colors for the time they switched on. Yay! Okay, so it's a game to sort of figure out what happens. Obviously, I is in trouble. But now they have, I think it's a third again. So now they have 9 friends. So they're going to need 9 to switch on. So this is what happens. It starts to march in towards them. Ridiculous. Right, so so this had 2 out of 4, so it's going to switch on. 1 out of 2, blah, blah, blah. This one needed 2. This one needed 1. This one needed, it got a lot. It's pretty bad. So these are going backwards, actually. So now we're in trouble. All of these have switched on, and then now I will switch on. Right. You can look at this if you Xfig, people. Oh, you wanted to, no, I ran out of ability to color small dots, yeah.
Like, look, you've got these whole branches that only have one pair of
Don't worry, the world will be dominated by bizarre apparel. So this one is next. These guys are all going to switch on. They're all hangers on to I. I is their, great inspiration, right? So like, yay, okay, we'll do it too. What's that?
that one branch will never change.
Here? Yeah, so this one is not going to, right, so, but
That one weirdo, one person that has boots.
if it comes in through here and it's going to have to switch here. These guys are just like, they've never heard of them. I don't know what these things are. So this is the situation, though. These ones are going to switch. It's an ignorance thing, right? These ones are going to switch next time. This is the first time they've ever heard of them. They're not aware of the rest of the world, right? So there's a lot to be said in this for thinking about how, for creativity as well, balkanization has some really good properties. I mean, we know this from history. And I'll show you some other evidence for that. But anyway, okay. So there's been some work by I think Gleason and others now to handle it if nodes switch off, but having them stay on is a big bonus for the analysis, right? So you imagine this thing, it's marching in, then some of them are switching off. That would make this really hard. Just gotcha. Like you just think, like this is sort of like you can sort of see, you could make an argument here, but if some of them switch off, you're like, oh my God, I have to accommodate that with some, something. I don't know, hard. But you can, all right. So this actually works for all sorts of contagion processes, not just that threshold model, although that's what we're somewhat interested in here. You can get, and as I said, you get the whole time evolution, because you get probably the node of time of degree k turns on it. Again, it's for random networks at time t. And so, yeah, actually you get it at the level of, you can generalize this, you can have all sorts of other networks, but just for sake of argument, for this kind of thing where we have generalized degree distributions, yeah, what's probably the node of degree k turns on at time t, that is something that can be done. You can handle asynchronous updating, which is a nice extravagance. Okay, but this is the thing I was talking about. This is how we figure out whether something spreads. It's expansion from a node, and really we think about edges. And we use edges in both of these calculations. And the extent of spreading is we think about contraction around a node. So it's really a nice, very different kind of approach. No? I'm not sure if you want to like attack the board with and make it disappear. So, okay. The analysis is fun, but I'm going to reserve it for another time. So, let me tell you about a few other pieces here. Yeah, see, badness. Yeah. Okay. All right. So this is going back to the what stuff. This is just the spreading on networks thing, right? So let's look at the fraction of, I think you can see this okay, but the fraction of nodes of different degrees that are on at time t equals 0 for successful spreading events, right? So we seed the thing, we let it run, we seed it, and we let it run, and we look at for all of these spreading events, we look at the degrees of the nodes that turned on at time t. So there's something that should be kind of clear once we go through it. So the ones that started the thing off, they have a slightly higher degree on average than the underlying degree distribution, because it helps to have a few more friends then, okay, but not hugely. And so this is a bit different to the Poisson distribution that's underneath it. This is a very sharp distribution, and that's 5 there. So the nodes that are on in successful spreading events that are really helping, this is again this 0.18 kind of situation, right? So if you're vulnerable if you have 5, 4, 3, 2, or 1 friends. These are the ones that really helped successful spread. So there's actually an accentuation of the 5s. So this should make sense, right? So 5s are vulnerable, but they also give you 4 new infected edges. So they're influential vulnerables. They're in between, right? So it's not this is an argument for to move away from the central character kind of story. This is about the mass now. The ones that really help things spread are the ones that can be somewhat easily convinced, but of course can maximally convince other people. It doesn't seem too bad a thing, but this is not how people have thought about this at all. So you see at time t equals 2, we still have that kind of same distribution, but we're getting a few of these higher degree guys popping up. And you see that it dies off again because 12 or 11 is hard, right? This is a situation where 1 in, so 10 is the next step up, right? So 2 out of your 10 friends are on, then you'll switch for some of these characters, right? But if you have 11 friends, then you need 3. So you need to get above 0.18, right? So 10 and then 15, they're big jumps. But again, the ones that have, if you do get ones that have 10 friends, that's great, right? Because they've been infected by 2 and then they get 8. So they're the best ones. Again, you get this, right? So it's not as if this is filling in like the 6s and 7s. It's actually the 10s that are really helping differentially. Whoops. Okay, so it keeps going. This is t equals 4, 6, 8, 10. You see this bulge here. Eventually, when we've got through to the whole thing, if the thing's still spreading, then it starts to look like just the underlying distribution of the network, right? Everyone's being infected. Right? But early on, this is about early adopters. For this kind of mechanism, the early adopters have this interesting kind of feature. Should make total sense, but it's not, obvious beforehand. If it was a simple disease spreading thing, you just want to find all the well-connected ones and just let it go, right? See, it's really hard. I mean, you need to know. I mean, the story in the end, I think, is you need to craft messages and build products that you figure out somehow will spread through average people, right? Away from you. I mean, that's really the principal thing. So you may find that you can get, people come back and say, I sent it to 20 friends and so on. That's okay, but you really need to find out about how it's spreading in the wild, what I would call the social wild. And that's the thing. And you need to craft messages and redo them. And ultimately, it means you have to not be malicious or people just won't believe it when it's further away because, now it's friends telling each other. And that's all built on social trust, right? And a lot of the mechanisms that people try to, get into that now, Facebook and so on, well, they're messing with that social trust, right? So, there's just a lot of knowledge you have to have about the thing you're spreading, the product, the population. You have to do a lot of research with that. But the mindset of going out and not just trying to find, yes, it's good if famous people get on, help you with your cause, but you have to somehow, it's very hard. This is why it's taken so long to get even near this, because advertising is, you got to measure something, right? So, but we can talk about that more. Yeah, it's a big deal. Yeah. I guess we've run out of time. I'm going to spread out. I'll finish this up on Tuesday. I'm going to talk about some more general results. What happens when we move to networks that have groups in them? Really different things. But now we can't do this analysis. The whole story with vulnerables, which is really important. So that's the takeaway for networks, that you have to have a vulnerable component. Thing spreads through it like a tinderbox, and then everyone, potentially everyone can get it. You can certainly have these robust yet fragile situations, which is very scary. But when you get out to other kinds of networks, more realistic ones that have groups in them, even more different behavior occurs. All right, so this is just part of the game. We got to figure out the basics, and that turns out to be pretty messy. All right, team. Okay, thank you.